Okay, hi everyone. In this video, we're going to take a look at finding confidence intervals for a population mean. But before I do that, I'd like to just take a second and go over our different types of data. So we understand when we're doing a population proportion and when we're doing a population mean. And so first of all, if we go way back to the beginning of the semester when we talked about different types of data, we had two types of data, categorical and quantitative. And categorical was things that were not countable. So for example, yes, no type questions. Do you like ice cream? Are you a boy or a girl? Do you enjoy going to horror movies or something like that? That's categorical data. And the way we quantify categorical data is by putting them into percentages, okay? And that's where we get into the P's and Q's. So for example, when we talk about P being the probability of a success, let's say the question was, what percent of community college students like ice cream? You would put that in the form of a question. Do you like ice cream? That's categorical data. But you take that answer, yes, and let's say you have 25 yeses out of 200 people that you ask, that is your p-value. That's your probability of success. So when we're talking about P's and Q's, we're talking about categorical data, we're talking about a proportion. We're talking about a proportion. So we would find a confidence interval for a proportion using categorical data. And similarly, when we have quantitative data, that is when we're finding a confidence interval for a population mean, okay? And that's just it. If it's quantitative, it's numbers. What is the average height of people? What's the average weight of people? What's the average blood pressure of people? What's the average time that somebody spends at work or something like that? If it's a numerical answer, you can tabulate a mean and a standard deviation. Secondly, I would like to just take a second and make sure we are clear on the difference between what is a population and what is a sample. Okay, so if you think about the population, that's sort of everybody in your study, and I'm going to write that up here. Let's say I think of this in terms of a circle. This is my population of people. I'm going to turn these numbers now into people. Here's my population. We're doing a study on something about college students. Do you like ice cream, or what's your average height, or what's the average number of hours you spend on homework? So here's our population of all community college or all college students. Okay, that's a population. In populations, if you are talking about categorical data, we have a population percentage of successes and a population percentage of failures. We have a population mean and we have a population standard deviation. And these are the symbols that you're pretty comfortable with, your mean and standard deviation. Okay, what's a sample? Well, a sample is when you're doing a study and you want to find something out about your population, but you can't possibly ask the entire population. So you take a sample. You take a sample of people, you take another sample of people, and so on. And within this sample, you have a certain number, and that's usually our N. It's a sample size. And then we do whatever study we want. We can actually collect data on samples. It's hard to collect data on an entire population. So if we're looking at categorical data, we would have a population, a probability of success amongst our sample, and that's where this little hat comes above our P, population, probability of the sample. So that's the difference between a P without a hat and a P with a hat. One has to do with our sample, one has to do with the population as a whole. And again, we take data on the samples to draw conclusions about populations. Same thing over here. When we are talking about a sample and we're talking about quantitative data, where we want to find out the average height of college students or the average age of college students, we collect data on a sample and we tabulate a mean and a standard deviation, and that's the symbolism here. A mean for a sample is an X with a line over it. The standard deviation for a sample is an S, and N is our sample size. When we're talking about the population, we use our mu to represent mean and the sigma notation to represent the standard deviation. population. And this is the one we're more familiar with. But these separations are now going to become very important when we talk about a confidence interval for a population mean. So we do intervals, we take data about the sample to come up with a confidence interval for the true mean of the population. And that's what we're going to be doing in this video. Oops, we didn't want to do that. Okay, the next thing I need to briefly talk about when we're talking about the confidence interval for a population mean is we're going to add a new type of distribution to our choices, basically. So at this point, we've been dealing strictly with the normal distribution, and hopefully most of you are pretty comfortable with that. And we know how to find a z-score when we're in a normal distribution. We take the whatever that x value is, subtract the mean, and then divide it by the standard deviation. And we talk about the standard deviation divided by the square root of the sample size. However, in this case, that's just basically our new standard deviation that we've been dealing with forever. So we always use our normal distribution when the standard deviation, and notice that this is a sigma, so this is the standard deviation of our population. When that is known, then we can always use our normal distribution to table. But sometimes our standard deviation of the population is not known, just like we don't know the population mean, which is what we're trying to find an interval for. Okay, so we take a sample and we compute a sample mean and a sample standard deviation. So we don't actually know the population's standard deviation. When that happens, the formula is still basically the same, except now we have to do what's called a t-distribution rather than a z-table. Now, I'm not going to get too much into the specifics of it. In general, a t-distribution is very similar to a normal distribution. It's symmetrical. It varies in that because you're talking about a sample standard deviation with every sample. Remember, the samples were inside of the actual population, so the population just has one standard deviation. But if you're taking a bunch of samples from within your if you're taking smaller samples with come on, pen. Now I'm not sure what's going on here. Whoops, there's my. Let's pause this, and there's my, okay, let's try again. If you're taking samples within your population, each one of these has a slightly different standard deviation. Hopefully it's not too far off the standard deviation of the entire population. But because you might have slightly different standard deviations, what do we have? We have more variability. And that's why the main difference between a t-distribution and a normal distribution is you'll notice that it's just a little flatter, okay? So you have to go farther out in terms of standard deviations to cover that 95%. We know with the normal standard deviation that our critical value for a 95% confidence is that roughly 2 standard deviations, but specifically 1.96. But for a using the t-distribution, and I'll get into this in a bit, this value is really going to depend on your sample size. That becomes very important, and we'll get into that in a minute when we start using the t-table. We'll talk about this in class. So you just have to use a little different table and a little different process to get your critical value. Okay, so let's tackle this problem. Okay, so just like in the previous videos, to find a confidence interval for a population mean, we have a set of steps to follow. And I'm going to go through each one of those, but first we are going to take a look at an actual question. So this is from classwork number 24, and we're going to just do problem number 26 together. And let's say we have, what the question says is, we have a laboratory tested 12 chicken eggs, and found the mean amount of cholesterol for that sample of 12 eggs, so n equals 12, that's the number of eggs that we took in our sample, Ab found the mean amount of cholesterol. It was 185 milligrams of cholesterol with a sample standard deviation of 17.6. So this 17.6 milligrams is the standard deviation of these 12 eggs that they looked at. From this information, we want to construct a 95% confidence interval for the true mean cholesterol level of all eggs. So we are trying to draw a conclusion. We are trying to find the mean of the population. What we have here, this 185, that is the sample mean. Okay, so let me jump back. I'm going to turn this off, and here we have our steps. So the first step says to state the sample mean, decide if you have a population standard deviation or a sample standard deviation, and therefore determine the model. We're going to use the t-distribution. If we've got a sample standard deviation, we're going to use the normal distribution if we've got sigma or the population standard deviation. All right, so let's jump back to our question. And let's do step one. Step one was state the mean, the n. So n, the sample mean and the standard deviation. So we have an n of 12. We have a sample mean of 185 milligrams of cholesterol, and we are given the standard deviation of the sample of 17.6 milligrams. And because it's an S and not a sigma, we are going to have to use the t-distribution. All right, so let's take a look at the second step. Second step says to check the conditions. I'm not going to spend a lot of time on this. Basically, if your population data is normally distributed, you just go ahead and move forward. If not, we need to have a larger sample size. We talked about that central limit theorem. Same thing just applies. So we'll just look at that. This doesn't actually state it. Doesn't really matter because actually n is not greater than 30. So we're going to assume a normal distribution, normally distributed population. And I would tell you that. If I'm not quite sure as to why it's not in the question. All right, step three is to find the critical value and error. Now notice here that we have two slightly different formulas, very, very slightly different formulas to find the error for the for using a z-table versus finding the error of using a t-table. Notice the difference. One is using the critical value from the z-table. The other is using a critical value from the t-table. Otherwise, it's the same. We are using the sigma or the sample population. So we're going to be using this one here. Let's go ahead and do that, and we'll talk about how to do that. So we're going to have to find the critical value. So the critical value is based on, my bad, 95% confidence. So we've got 95% confidence. And we have what's called something called degrees of freedom, and that's equal to n minus 1, which in this case n minus 1 is 12 minus 1, which equals 11. And we're going to go to the t-table, and that will tell us that the t value is, let me pull up a t-table here. Okay, so here is our z-table, our t-table, I apologize. And you'll have you should have your own t-table. We're looking at 95% and confidence level. So notice that that's right up here at the top. And here are our degrees of freedom. Rather than a z-score, we have something called degrees of freedom, which is just n minus 1. You can write that right on your paper. And we had n equaled 12, so we're actually going to go here to 11. Here's 11, and we're just going to follow it right over to our 95% confidence, and it's 2.201. Okay, 2.201. So we're going to close this one out. We're going to reopen this one, and our confidence level is 2.201. And you'll notice that that's a little bigger than a z-score at 95% confidence, which was 1.97. And that's the reason, because it's a little more spread out. We have to go farther out in our standard deviations to cover 95% of the population. Okay, and that's really the only difference. So using that now, we find the error to be the 2.201, our critical value, times the standard deviation, sample standard deviation of 17.6, divided by the square root of the sample size, 12. If you put all that into your calculator, you will get 11.18 milligrams. So that's that error, just like we did in the confidence interval for a population proportion. Again, what we're doing is we're looking for an interval. We're looking for some sort of interval. Our sample mean is right here. Our sample mean is right here of 185 milligrams. That's how much cholesterol was in our sample. So we're trying to find how much cholesterol, what's the average amount of cholesterol in all the eggs. So we're looking for sort of these boundaries, these intervals. And so what we've computed here is this error, which comes from the standard deviations. How far out do you want to go times what the standard deviation is. Okay, and so this is our error here of roughly 11 milligrams of cholesterol. So step 4 is then to step 4 is to find the confidence interval. So you'll notice the steps are very, very similar to population proportion. So our confidence interval is going to be the mean, the original mean of 185 minus the error. That's the lower boundary. And that, again, we've got our betweenness. The actual mean lies between these two boundaries of 185 plus the error. And if you do that on your calculator, you're going to see the lower boundary is going to be 173.8 milligrams, and the upper boundary is 196.2 milligrams. Okay, so that means this lower boundary is about 174, this upper boundary is about 196, and so the true mean is somewhere in this range. We're 95% confident that the true mean of the population is somewhere in here, somewhere in this range, between 174 milligrams of cholesterol and 196. So the last step, of course, is just stating that conclusion. You can see the last step, just like with the population proportions, is to state your conclusion. So in our final step, we're going to state our conclusion that we are 95% confident that the population mean, meaning the whole mean, of cholesterol levels for all eggs is between 173.8 milligrams and 196.2 milligrams. So again, what we've done is used sample data to draw a conclusion with a certain amount of accuracy, because we can never be 100% about any exact mean, but we use the sample information to come up with a range or an interval for the actual mean. So very useful stuff. All right, go ahead and continue with classwork number 24.